Planning and executing an efficient descent from your cruising altitude into your destination is an absolutely critical part of what it means to be a pilot. From a civilian standpoint, whether you're flying GA or commercial, a fuel-efficient descent means more money in your or your company's pockets. However, from a military perspective, the more fuel we can save on the en route portion of our sortie means more fuel that we can spend on station helping out the guys on the ground. When it comes to actually executing an efficient descent, the primary tool by which you'll execute this will be using the ADI method. In order to execute the ADI method, you'll need to know the distance to your destination and the amount of altitude that you need to lose in that distance. Once you have this information, put the distance to your destination on the 10 degrees nose-low reference. Then you're going to put the altitude to lose in thousands of feet somewhere on the ADI as a fraction of the distance to lose. So a 2.5 degree nose-low descent would be a quarter, 5 degree nose-low descent would be half, and 7.5 degree nose-low descent is going to be 3/4. For example, if we had 20 miles to our destination and we needed to lose 10,000 feet, I would put 20 nautical miles on the 10 degree nose-low reference, and then 10 over 20 as a fraction becomes 1/2, which means that 10,000 feet would go on the 5 degree nose-low reference. In effect, I just calculated that if I want to descend 10,000 feet in 20 nautical miles, that I need a 5 degree pitch change from my current attitude. Likewise, if I had 50 nautical miles to my destination and I needed to lose 20,000 feet, well, 2/5 is about 40%, which means that I need a 4 degree pitch change in order to effect that descent. Another less common example would be needing to lose 15,000 feet in 10 nautical miles. Well, with 10 nautical miles being at the 10 degree nose-low reference, 15,000 feet would actually put me at 15 degrees nose-low, which means I need 15 degrees of pitch change in order to make that descent. We can approximate our desired VVI by taking our ground speed in nautical miles a minute, so divide your ground speed by 60, and then multiplying it by that degree pitch change. So if my GPS tells me I'm doing 240 knots on the ground, and I calculated that I need a 5 degree descent, 240 divided by 60 gives me 4. 4 times 5 is 20. Multiply 20 to make the math look right, and that gives you a 2,000 foot per minute descent in order to make that happen. Likewise, let's say we calculated a 15 degree descent, so 15,000 feet in 10 miles, and we're doing 180 knots on the ground. Well, 180 knots divided by 60 gives me 3 nautical miles a minute. 3 times 15 is 45 times 100, so that means I need 4,500 feet per minute descent in order to make that. That right there is the most basic foundational knowledge that you need to know in order to have an efficient descent from your cruising altitude. These numbers are all approximations, so as we continue our descent, we need to continuously update to make sure that we are getting the proper performance and that we're executing that nice, good, efficient descent. It's also worth noting that this math works in the opposite direction as well. If I need to make a climb restriction, and let's say that I have 10 nautical miles to go and I need to gain 5,000 feet, well, guess what? 10 nautical miles goes on my 10 degree nose high reference. 5,000 feet is a fraction of that, which means that I need to be climbing at least 5 degrees nose high. And then I can take my ground speed and do the same math as before to calculate a desired VVI in the up axis in order to make that climb restriction. Using this math allows us to let ATC know whether or not we can comply with their instructions as early as possible. And the earlier we let them know that we don't have the performance to do what they want, the easier it is on them and everybody else to make things happen to ensure everybody's safety. Now that we have the basic fundamentals and the math out of the way, now on to the critical thinking portion of an efficient descent. So let's say we're cruising at 25,000 feet and we're 100 miles away from our destination. If the approach controller tells me to descend and maintain 10,000 feet, all you have to do is calculate 25 as a fraction of 100, which gives us 2.5 degree nose-low descent, and then just execute a 2.5 degree nose-low descent from 25 down to 10,000 feet. If you're nice, slow, and controlled, you'll most likely get a lower altitude prior to actually hitting 10,000 feet. When executing these very shallow descents from over 100 miles away, It's important to remember that if you're told to descend, that you owe the approach controller at least 500 feet per minute on the descent. So if your calculation gets you less than 500 foot per minute, just go ahead and give him 500 feet per minute, or if fuel is absolutely a factor, tell him you're unable for fuel. The next thing to consider is that you're typically not going to descend from the flight levels straight into landing. You're probably going to have to shoot an instant approach. So instead of descending from 25,000 feet down to 0 feet, we're going to descend from 25,000 feet down to our final approach fix altitude. So now let's say you're cruising around at 25,000 feet. You're 50 miles away from the Sea Springs Airport, and you want to shoot the ILS to 17 lift. Well, looking at the FAF altitude, it's 8,700 feet, so let's just make the math easy and call it 9,000 feet. So 25 down to 9 gives us about 16,000 feet and 50 miles to lose. Well, I know that 1/5 is going to get me 2 degrees nose low, and 2/5 gives me 4 degrees nose low. So a good efficient descent is going to be somewhere around 3 degrees nose low to get from 25,000 feet down to my FAF altitude from 50 miles away. To add another layer to this equation, our thought calculus is going to be a little bit different if we're already aligned to the runway, or if we're coming in opposite direction of where the field is taking off and landing from. So in this example, Sea Springs is landing runway 17, so they're currently south flow. Well, what if we're coming in from the south? Well, that's okay. I usually like to descend to my FAF altitude by the time that I'm passing the field that I want to land at. That way, if they want to slam dunk me, I don't have to worry about adding in a descent while also getting all my checklists in. I can just focus on getting the vectors and just getting my gear and flaps down, getting on speed, and flying the approach. However, if the Springs is south flow and I'm coming in from the north, hitting the FAF altitude at the field is no good because I need to get to the FAF altitude by the FAF. So a good rule of thumb is that final approach fixes are typically 5 miles away from the field, and I want to be down 5 miles before the FAF. So right off the bat, I'm thinking napkin math, 10 miles prior to the field, I want to be at my FAF altitude. However, looking at this approach, it appears as if the FAF is about 8 miles from the field. So I want to be down 5 miles before that. So I need to be at the FAF altitude 13 miles prior to actually getting to Sea Springs Airport. So same situation as before. I'm 50 miles from Sea Springs. I have 16,000 feet to lose, and I'm coming in from the north. So first of all, I'm going to subtract about 10 miles from 50 to make the math easy. So I'll say I have 40 miles to lose 16,000 feet. Same concept as before. We want to use very simple pilot math. So we know that 10,000 feet and 40 miles is 2.5 degrees nose low. And we know that 20,000 feet and 40 miles is a 5 degree nose low descent. So 16 should be somewhere in between. So let's give it about 4 degree nose low on the descent and then see how it works as we continuously update ourselves into the field. So everything we've discussed so far is what to do if you're directed to descend. Typically speaking, if fuel isn't a factor, you should just go ahead and comply with their instructions and calculate that efficient descent the way we already discussed. Now let's talk about what to do if you're given the option as to when you want to descend. This is also known as a pilot's discretion descent. In simple terms, the approach controller is telling you that you're cool to cruise at your current altitude, but if you'd like to descend, you can go ahead and do so. You just gotta let them know that you're doing it. As a general rule of thumb, most aircraft can descend efficiently at a 3 degree nose low descent. Likewise, if you're carrying passengers, most passengers won't notice or be alarmed by a descent rate of about 3 degrees. So the simple math for a 3 degree nose low descent is to descend at 3 times the altitude to lose. So if I'm cruising at 25,000 feet going down to sea level, 25 times 3 is 75. So I need to start my 3 degree nose low descent at 75 nautical miles from the field. If you want to go even shallower, a 2.5 degree nose low descent is approximately 4 times your altitude to lose. So 25,000 feet down to sea level will give us about 100 miles out. We need to start our descent. As we discussed before, the same rules apply when it comes to talking about whether or not you're already aligned with the runway. So If they are landing to the south and you're coming in from the south, yeah, go ahead and start your descent at 3 times altitude to lose. But if they are landing to the south and you're coming in from the north, do 3 times altitude to lose plus 10 to allow you to get down to your altitude 5 miles prior to the FAF and get configured. So that's everything you need to know about calculating an efficient descent into a field on the fly. Now let's talk about a pre-planned descent. Typically speaking, we're going to calculate and execute a pre-planned descent when fuel is a factor. So I'm thinking very long range legs, or if there's a lot of weather that's driving us to use an alternate. So in the mission planning phase, what we can do is we can look at the performance data and charts in the back of our Dash 1, and we can calculate a max range or en route descent. So these charts are pretty simple. This is the en route descent chart. Let's say we're cruising at 25,000 feet and we're going down to sea level. We just go down and see that we want to descend at about 25 miles out, which is a 1-to-1 descent, which is 10 degrees nose low. So if fuel is getting tight or a factor, well, I'm not going to start my descent out at 25,000 feet until I'm 25 miles from the field. That will ensure that I can get in nice and safely with plenty of gas to spare. Likewise, as a personal technique, I never plan to execute a maximum range descent, but I always am aware of what my maximum range descent profile looks like. So for the T6, that's going to be 180 knots with a 1500 foot per minute descent. If you run the numbers from 25,000 feet, you see that you need to lose 25,000 feet in about 60 nautical miles. Again, using simple pilot math, I know that 30,000 feet to lose in 60 miles is about a 5-degree nose-low descent, so 25,000 feet in 60 miles is going to be something slightly shallower than that. So we'll go out the door saying 4-degree nose-low descent. And there you go. That's everything you need to know about how to think about and execute a fuel-efficient descent from your en route altitude on into the airfield. Again, most of these were all personal techniques, but the most important thing is that you're actually thinking about these things and that you have a why behind all the stuff that you do in the aircraft. Until next time, I will see you later.